Hi, everybody. Thanks for joining our session today on active galactic nuclei, 1 of 2. Our second session is this afternoon at 2 p.m. Eastern Time in the US in the Chandra Frontiers in Time Domain Science virtual workshop. Today we have 3 speakers for you. We have an invited talk and 2 contributed talks. And our first speaker, if they can start sharing their slides, is Maurizio Paolillo from the Università di Napoli Federico II, who's going to talk to us about monitoring AGN variability over 2 decades with Chandra Deep Surveys.
Hi, I hope you can hear me.
Yes.
You hear me fine? Okay, great. So I thank the organizers for this opportunity. And actually, I am also replacing Francesca Seyfert, who I should thank. She was supposed to give the overall review on long-term variability, and she couldn't be here. So we arranged the presentation together. So what I'm going to talk today is about the long-term variability AGN, mainly taken from long-term surveys, and in particular the Chandra ones. So let me start to introduce why we're interested in variability. Clearly, variability in AGN is a powerful discovery tool. AGN have been discovered also because of their strong variability. But there are a number of things that the variability allows you to do. Of course, to understand the structure of the object that you're emitting, and this was one of the clues that these are small emitting regions, and so with that had to be powered by a supermassive black hole. And then you can study the physics, because the variability gives you the time scales and the sizes of the region that you're looking through. And then, of course, you can use it also to constrain the duty cycle of the activity, which is very interesting in terms of evolution. For instance, and we know that AGN are variable all across the electromagnetic spectrum, but relevant to this talk is that they are the variability is a byproduct of most long-term surveys. So if we do deep surveys, most of the time we also have, we are exploring the timing domain. So in one thing I will not concentrate in this talk is the very long variability, which is related to the duty cycle of AGNs. We know that AGN go through activity phases, and they can have periods where the activity is very intense, maybe following mergers with some delay. And so this recently has been called variability in a broader sense, but it's not something that we can see on short time scale. Sometimes we can see it using, for instance, light echoes, like in this nice example in which we see light echoes of the past activity of the quasar in this galaxy, or in cavities in X-ray clusters in which we see the remains of the past radio activity of the central AGN. I will not focus on this. I will instead focus on the properties on medium long-term variability. And nowadays we're interested in trying to see if the properties of AGN and quasars evolved through the universe. And we're starting to try to understand if also the variability properties evolve. For instance, we know very well now that the spectra of quasars are pretty stable across the known universe. The spectra are almost consistent with each other, even out to very high redshift, out to redshift 7 or so. And the emission light widths are similar. And so this seems that the fundamental mechanism is the same. What is still missing is the variability. The variability is a bit more complicated to assess. So in this plot that I will show again later, there is a plot of the fractional variability versus the luminosity of the sources. And you have to compare this with models. You expect an anti-correlation. So you have to compare this with models because, as I will show you, The variability depends also on the time scale, the wavelength that you're probing. And so it seems now that AGN behave consistently, even in terms of variability, although there are still cases like this Swift sample out here, which seems way off the models that predict variability. So there are still some issue to cover to understand what exactly is going on. So the behavior of AGN that we know so far are that AGN vary at all wavelengths. So in this plot here, you can see how from the X-rays to the optical bands, the AGN have a similar behavior, although as you move to higher energies, the variability on short time scale increases. So it is clear that there is some additional variability which is superimposed on the long-term variability that you see in the optical, for instance. And this has been interpreted with different models. There are a number of models that here I listed, from the simplest one, the variation of a single region, which are now ruled out, to the shot noise variability, to the more recent one, which discussed variability in terms of variation in both the accretion rate and instabilities in the accretion flow. What is emerging is a scenario where probably the variability in the disk is the superposition of components produced at different distances from the central black hole, and this will modulate in a multiplicative way the variability in different wavelengths and on different scales. So which then superpose to each other and modulate the final scenario that we see all together. But here I will not discuss the rapid variability. There are other talks that will do that later. And I will just point out in terms of the characteristic timescale that whatever the actual physical mechanism is, which we don't really understand in detail nowadays, both if you take dynamical timescales of the disk, if you take thermal timescales, if you take a viscous timescale, in all these cases, you will have some dependence on the black hole mass. And in some cases, you will have also dependence on, for instance, the scale height of the disk. And these in terms can relate to the accretion rate. So we have a reason to believe that the physical properties of the central engine will be reflected in the variability. And in fact, for a long time, looking at variability long time scale, we modeled the power spectrum of AGN, which something that resembles a sort of a power law. So here I'm showing you a schematic in which there is the frequency on this axis and the power emitted by the AGN. So this is a typical red noise spectrum in which you have increased variability on longer time scales. And you have, of course, a white noise level. The interesting thing is to try to understand if there is any feature in this power spectrum, because if it's just a power law, it has very little predicting behavior. There are a lot of processes that will produce a power law, but it's interesting you find some characteristic time scale, for instance, a break in this power spectrum that is, it's reflecting some intrinsic property of the black hole. And let me just point out that here I'm presenting this in terms of power. So you will see a broken power law, but from now on, I will show you this in terms of power multiplied by frequency, which will flatten out this part. So something that will be with this slope will become more or less flat. So what do we see in actual AGN? We usually see something of this sort. So here is the frequency, the power per frequency. And now we see that in several nearby AGN, several tens of them nowadays, we are able to see that the power spectrum follows a broken power law. And so there is a characteristic time scale. And actually, this seems to scale with the mass of the supermassive black hole. Larger black holes have longer variability time scale, which are expected given their larger sizes. So in this scheme, we know that there are already some quantities which relate to the power that we can measure in in the supermassive black hole. But since 2006, from the well-known McCarty paper, it was shown that actually you can build sort of a fundamental plane of variability of AGN if you take both in consideration both the mass of the supermassive black hole and the bolometric luminosity, which is considered as a proxy for the accretion rate. So once you fold both of them into this model, you can predict what the expected time scale of this break will be and compare with the observed one. And the amazing thing is that this prediction holds all the way down to stellar mass black holes, which would mean that the variability of black holes are similar all the way across 6-7 orders of magnitude at least. So how do we deal with this if we want to take very long look at AGN? And these are usually the byproduct, except for a few nearby AGN, of long surveys. So to get this type of power spectra, we usually need something that is of this type. So these are XMM light curves and or RXT light curve. And here you can see that to get a good power spectrum, you need very long continuous observation with very good sampling. And most often you need many of these because variability is intrinsically stochastic. So if you repeat the observation, you will never get exactly the same thing, and you have to average multiple observations of the same source. So this is prohibitive to obtain in large surveys. So a more simpler approach is needed if we want to investigate in variability in large survey. And the approach is to do something that it's more of an integrated view of the variability. So it was recognized early on that, as I already showed you, that the variability, the sigma, in this case, we're using these excess variance, which is basically the RMS scatter that we measure in the light curve corrected for the statistical errors, is anti-correlated with the luminosity of the AGN. And this has been interpreted in terms of an anti-correlation because between, again, the variability and the black hole mass. But at the same time, so this trend that you see, this anti-correlation, comes from the fact that if you're just measuring RMS, what you're actually measuring is the integral of the power spectrum. So here there is a schematic of the power spectrum, and you're measuring the integral between the minimum and maximum time scale that you are probing. So if the power spectrum changes in the sense that the break moves, then you will observe different amounts of variability. And this is what produces this anti-correlation. At the same time, there are objects like, for instance, narrow line Seyfert ones that show increased variability in general with respect to the average AGN population. And so in these cases, you can think that this is related to a change, for instance, in the accretion rate. And if this would imply a change in the normalization of this power law, you would get that this is another way to change the RMS of your variability, both if you sample this part of the power spectrum. So this is the approach that is being taken for long surveys with low statistics, few photons. And there are a number of issues with this, that of course you don't have many repeated observations of the same object. So I show you, for instance, this is a simulated light curves of one, for instance, long XMM observation, in this case, that we were producing. And you see that if you sample just a piece of this light curve, you will get an average value that is not necessarily the one that reflects the underlying average of the whole light curve. There is an additional problem if then you don't sample the whole part of the light curve between two points in time, but you have chunks of observations. And the scatter will make everything more complicated. So to understand how to correct for this effect, you will need to do simulations and assume some model. And what has been shown, and we work on this for for some time, a few years back, is to show that basically the individual measurement on a single AGN have very little meaning because it's stochastic nature. But if you average enough pieces of a light curve or enough sources, you can get a pretty well-behaved probability distribution. But you will still have biases in your measurements. And so you have to come out with some prescription to correct for this bias. The bias is basically the observed variability versus the intrinsic one, because otherwise you'll never be able to go back to the actual models that you're observing. So what do we actually observe? So when I joined this field, I started working on the Chandra Deep Field South. At the time was the first megasecond observation. And the idea was to try to look at the variability of AGN in this 1 megasecond. And what we found was that we could confirm this anti-correlation between X-ray variability, X-ray luminosity and variability. However, we were finding that high redshift AGN tended to be more variable than low redshift counterpart. To be entirely honest, this was not a new finding. There was a finding from Rosat data that was showing something similar. But the problem is to try to understand if these effects are real or are due to biases because of how your light curve are sampled. And this is a long-standing issue that it's very complicated. So this is just an empirical line that that goes through the points, has no physical model. So if we want to connect this to some physical model, still empirical because we don't know what the physical model is, we can do something like the work that Papadakis did in 2008 and look at create somewhat more realistic model which follows the McCarty prescription that I showed you before, and again look at the variability versus the X-ray luminosity and show that a more realistic model in which there is dependence on the black hole mass and the accretion rate will produce some model with the bending, because at some point you're sampling above the break frequency in the power spectrum. And the point here was again that going to higher redshift, you would have, you would have to shift your model up to higher accretion rate to account for the increased variability. So a picture was emerging that we were being able to trace both variability and black hole mass. So basically, this is a sequence in black hole mass along one model, and then if you shift the model, it's because of the accretion rate. However, if you look at other samples, like the one observed by, for instance, by Gabriele Ponti in 2011, the Caixa sample, which is a local sample of AGN looked with XMM more detail, in that case, you have an advantage. The advantage is that you have black hole masses measured for this object because they're low redshift. And so now you can see that actually you don't have to infer from luminosity, but you actually have these this anti-correlation. But to account for what was observed in terms of luminosity, they needed to not only to change the accretion rate, but only to change the normalization of the power spectrum. So the models were becoming more complicated. To make things worse, in 2012, Gonzalez, Martin, Vaughan revisited the McCarty result and looking again at the sample of local AGNs, and they claimed that, well, you don't really need the dependence on the break time scale from both black hole mass and accretion rate luminosity. You can just even fit it with the black hole mass. So with the conclusion that there is weak or no dependence on accretion rate. So what is the real underlying mechanism started to be debated. Another step forward was with the Cosmos field. Now, Cosmos field is another one of these high redshift survey that was not designed originally for variability. However, as you can see here, at least in the Cosmos, in the XMM coverage of the Cosmos field, you can see that there are many epochs spread over several years. And so you can sample a distribution of timescales and look at variability of this source. The unfortunately, in this type of observation, most of the sources have very few observations, 4 or 5 observations only. And so this makes the task very challenging and produces distribution that have an enormous scatter. And this is just expected by the fact that you're randomly sampling a stochastic process in a very sparse way. But still, again, here we found an anti-correlation with black hole mass and almost no anti-correlation with Eddington ratio. So what could be done better than that? Well, actually, all these surveys are built over time. So if we look at the deepest one that we have for Chandra, will remain probably the deepest one for a while, is the Chandra Deep Field South. So the Chandra Deep South over the years, starting from the first megasecond from 2001, has accumulated more data. And here I show you a movie on how the survey has been built in time, accumulating exposure time. And on the right, I show you a zoom in on how the signal to noise increases. This is renormalized to the average background level. And you see that source pop out as the time goes by. So as we accumulate it down to 7 megaseconds, you clearly see the effect of adding more photons. Of course, it becomes increasingly challenging to go deeper as you have more and more exposure times. But this is the cumulative view of one of deep survey. Every one of these survey has a differential view because you can, instead of stack all the observation, you can look at them resolved in times. And this is what I'm showing you in this other movie, in which we played a little bit with the PSF to homogenize the PSF across the field of view, but this is showing you the actual variability of the AGN in the Chandra Deep Field South as they've been observed from 1999 to 2017 over the second megasecond. And you can clearly see that they switch on and off. Some completely disappear. Of course, the faintest one are a bit affected by noise, but even several bright ones, increase and decrease in luminosity clearly. So this is a Christmas tree, and all AGN are clearly strongly variable. And this is an example of the light curve that you get, which have a sparse sampling because it depends on when we did the observation. But there are chunks done of more or less continuous observation. So with this type of data, you can do different type of things. One thing that you can do is to put them together. For instance, the work that Monica Young did in 2012 with the first 4 megasecond was just to bin in 4 large bins, the first 4 megasecond, and look for low luminosity AGN. The one that you see down here in black are sources that are variable, but they are below the average, the average optical to X-ray ratio that is expected from AGN. So these sources would be classified as normal galaxy, but we see them variable in the X-ray, so we know they contain AGN. So you can discover a population of these faint sources. The other thing you can do is, of course, look at the overall variability. So again, you now have the luminosity variability anti-correlation. Now you can see that the dependence on redshift has disappeared. So now that we have a much better sampling of this object, we can see that most likely the variation with redshift depend on the fact that we had biased sample and we were not properly sampling the high redshift sources. But now you have much more information. So you can take your light curves and then you can use different parts of them to sample different time scales. So this is what we try to do to get a better modeling. And the thing you will find is that the first thing you can ask the question, do high redshift AGN have the same property as low redshift one? Do they have a bending power spectrum with a slope between -1 and -2? And this is a line of -1, while this is what you observe for the source in the Chandra Deep Field South. So you need a bending power law with a slope similar to the one you see at low redshift. You have different models here because at every redshift, you're sampling different time scales. So you need the model to follow what you're actually observing. So now if you try to put all together the redshift coverage that you have, the different time scales, you can put all together to try to model simultaneously the redshift ranges, the 4 different time scale, and the luminosity interval that you have. And this is what we did 3 years back, trying to push the model. You can see how large are the error bars. This is due to the random, the stochastic nature of the source, the fact we have few sources in such a small field. But we were coming out with the prediction that the best fit model, here every color of the model has to fit its own data, which are the one with the same colors, because each sample is at different redshift, so sample different luminosities and different time scales. And so you could tell that with 10% confidence, we thought that we had both dependence on black hole mass and accretion rate. And so this will, this opens interesting possibility of tracing the black hole accretion across a long time scale. So let me go show you that these large sample of X-ray sources are also needed to, for instance, in Cosmos, to assess how well variability will perform, for instance, in the optical with LSST. This in the Cosmos field will show that optical variable source represent a subset of the X-ray variable source. And so this is important to assess the purity of the sample and what is the completeness and the biases that you have. Still, X-rays are the best indicator of the presence of nuclear activities. But there are other things. You can look at the optical to X-ray ratio, for instance. This is a work done with archival data from XMN. And you can see that this UV OX luminosity has a large scatter, even when you take simultaneous observation of object. Why is this interesting? Because you may have heard that lately there are studies that are creating, oh, sorry, my presentation got stuck. Not moving to the next slide. So what I'm going to show you as soon as it moves to the next slide is that there is, we're building Hubble diagrams of with quasars and also gamma ray bursts, which are suggesting now that at the cosmological level, that maybe the lambda CDM model is not the correct one. And so this has been, so this is the famous quasar diagram by Lusso and Risaliti, and which shows a 4 sigma tension with gamma ray bursts. But variability is the key ingredient in explaining the scatter, so you need to take that into account. And let me also show you that now we're putting together all these data set. And so if you take all archival data, XT, Cosmos, Chandra Deep Field South, and Kasha, it seems that we can trace variability with this deep survey, and they so more or less behave well, and we're starting to constrain the dependence on the physical parameter. So what can we do for the future? We can look, since we don't have any very larger mission coming in the very soon, we can look at the archive. So this is, Francesca gave me a plot of all the sources in the Chandra archive and how many of these observed multiple times in every observation. So if you combine all this wealth of information you have in the archive, you can have thousands of sources with more than 50 observations spanning over 14 years. And you can even combine them with other archives as long as you take into account the cross-calibration issue, which are not simple, but they're there. And on the other hand, I'm sorry, this one, okay. There are missions that are going to fly soon. For instance, this map is showing what the future EXTP mission will do with the large area detector. It will cover all the sky. It will have low resolution, so it's good only for nearby EDM, but there are regions of the sky where you will have hundreds of variable sources observed at least for a quite long exposure time. So you will have tens of observations for these sources. Of course, there's some mission that is already doing this, which is eROSITA. eROSITA is scanning the sky now. And so in 4 years, we'll have covered especially the poles, with very deep observation, at the same time allowing to do variability with very large sample observed over several epochs. And this could even bring us to do directly cosmology with variability if we are able to measure, for instance, the variability and using scaling relation derive the luminosity of the object directly from variability. So mission like, for instance, the Star X, which has been proposed, are mission that with a large field of view will and a larger effective area than what has been flown so far, and hopefully a good PSF will be able to do this type of survey and increase the sample size that to this day are very limited, very small area. So let me conclude saying that we have this multi-epoch offer allows us now to study long-term variability of the distant AGN population. We're starting to get a pretty good handling on the luminosity variability correlation, the dependence on the mass. The dependence on accretion rate is still debated, but they seem to follow the same physics at every redshift. Of course, we need larger samples because here we're really photon starved and biased. And so the hope is the wide field multi-epoch mission will allow to push forward toward a high redshift universe. Thank you.
Thank you, Maurizio. If you have any questions for Maurizio, please enter them into the Q&A box. We have a question from Agniva. In most excess variance versus black hole mass or elbow plots, we see extreme scatter. How justified is it to do a linear fit?
It is not linear at all. You're correct. It's in fact the correct model is even if we use some empirical model, is a bending sequence, is not linear. It has always been done linearly. There is a sort of linear anti-correlation, but at some point you're crossing the break in the power spectrum, and so it's not linear anymore. This is according to this empirical model. Now we don't really know the detailed physical model. So the one that I showed you before, let me see if I can go back to one of these models. And you always have something that has a break and will bend. And this is already a step forward. So now the fitting is done with this type of models. But as you said, because of the scatter is so large, until we can constrain better with larger sample the average variability, the difference between a linear model and a bending model, it's becoming sensitive now. With the latest sample, we are sensitive to the bend, but before there was very little sensitivity to that.
Great. So it seemed like some of the observations you showed us where you're building up really deep exposures and you're monitoring or quasi-monitoring a source over, I would say it looked like decades. Is that right?
Yeah, the Chandra Deep Field South is 17 years of observation. So now we have a pretty long baseline, some of these.
So for future missions that you want to maybe do something similar like this, would you have to wait a while to build up similar data, or you feel like you must merge with existing observations to?
Yeah, well, unfortunately, you will have to wait a while. There are things that help you. The fact that if you sample a broad redshift range, it will allow you to sample somewhat different time scale for nearby and distant AGNs. But to probe the low frequency part of the power spectrum, you really need to go on years time scale. Otherwise, you're not sensitive and you have a lot of degeneracies in your model. Cannot really constrain. So using everything we have in the archives is crucial to that, to extend the baseline and constrain, for instance, the low frequency part, and then we can have more leverage on the other parameters. So unfortunately, we will have to wait some time, but there are things that are already there that we can exploit to move forward.
If we have any more questions from our attendees, also if the panelists have any questions for Maurizio, just raise your hand because you cannot use the Q&A box, unfortunately. No, okay. Thanks again, Maurizio. That was an excellent talk. thank you for stepping in there also and including material from Francesca. I'm sure that she appreciates it. Okay, our next speaker, if they can start sharing their slides.
Share, here we go.
Our next speaker is Dirk Grupe from Morehead State University. Is going to talk to us about Chandra observations of the broad line absorption line AGN narrow line Seyfert 1 galaxy WPVS 007.
Yeah, and you probably think 007 has something to do with James Bond. It has not. No, it's a long name. It comes from a catalog, from an optical catalog, and this source was discovered basically in the Rosat-Orr Sky Survey, and I get to this in a second. It's a long title because we are talking about a very unusual object that connects broad absorption line quasars together with narrow line Seyfert 1 galaxies. And this was an idea that was first proposed by Neil Brandin, the famous narrow line Seyfert 1 meeting in December 1999 in Bad Honnef. Some of you may have attended that meeting. And I was really intrigued by that talk because he was saying, okay, there might be a connection between broad absorption line quasars and narrow line Seyfert 1 galaxies. And I was working on particular on narrow line Seyfert 1 galaxies. And this source was one of those examples for narrow line Seyfert 1 galaxies. Now, this suggestion was then also confirmed by findings by Todd Borason in 2002, where he said, well, broad absorption line quasars and narrow line Seyfert 1 galaxies, they share one thing together, and that is they are both high L/L objects. So relative to their black hole mass, their accretion rate is very, very high in both of these sources. The difference is that the broad absorption line quasars are very massive black holes with something like 10 to 8, 10 to 9 solar masses, while the narrow line Seyfert 1 galaxies are on the lower scale here with millions of solar masses, or maybe 10 millions of solar masses, which puts them, when you look at the mass accretion rate on the lower limit, so you accrete much less in absolute values, while the broad absorption line quasars, let's say they accrete something like several solar masses per year, while the narrow line Seyfert 1 galaxies, they are more like maybe 100th or maybe 10% of a solar mass per year. So they are on a different mass spectrum here. So what I did then also some years ago, together with John Nursak at Penn State, when I was still at Penn State, at the Swift mission, at the Swift Mission Operations Center, was to combine Chandra data of broad absorption line quasars together with Swift observations of those, because they will allow us to give us the spectral energy distribution of those sources. So we can directly measure actually the bolometric luminosity and compare it to the black hole mass and derive the L/L ratio. And this plot is a little bit weird because usually, it's like in a Hartree-Russell diagram where the temperature runs from increases from the right to the left. This is the same thing here. The L/L increases from the right to the left, and the same thing here. The accretion rate, the mass accretion rate increases from the top to the bottom. But this is exactly that corresponds to the plot that Todd Borason put in this plot, and we see that Todd Borason was absolutely right. We have the narrow line Seyfert 1 galaxies in this corner, which means those are the ones with the low L/L Eddington, but they with the low mass accretion rate, but they have high L/L Eddington rates. And when you look down here, these are the broad absorption line quasars that we studied in this study with the Chandra observations compared to the Swift observations. And these are the sources down here. When you look at these magenta stars, all these cyan crosses, these are also broad absorption line quasars, and they fall basically in the same category. So they have high L/L Eddington, but you have very high mass accretion rates. Now, when you are dealing with high L/L Eddington objects, these will produce radiation-driven winds. So you have an accretion disk that is very hot, that is very luminous, and you drive winds out of this, and because of the rotation of the material, you will get this structure that is in the famous Martin Elvis plot here from 2000, where you have the material flowing out towards you. You get velocity of something like 10,000 kilometers per second, or even 20,000 kilometers per second. And when you look from this direction, you look directly into the outflowing gas that comes towards you. This is what we see typically in a broad absorption line quasar. And the question is now, so if these are all high L/L Eddington objects, and we see these outflows in broad absorption line quasars, then we should expect something like that also in a narrow line Seyfert 1 galaxy. However, there was also the paper by Brandt and Laor, or Laor and Brandt, that said, well, the broad absorption lines should only occur in very high L/Wellington objects, in a high massive AGN, in black hole masses with something like 100 million solar masses. Now, WPVS 007, and this is why this object is so interesting, is maybe the link between these narrow line Seyfert 1 galaxies on one hand and the broad absorption line quasars on the other hand. Optically speaking, this is a typical narrow line Seyfert 1 galaxy. So you see the narrow H beta line here, you see the strong ion 2 emission, weak O3 emission. So it gives you the typical Borison and Green eigenvector 1 correlation, where if you have a strong ion 2 emission, you have weak O3 emission. So this is very, very typical for these narrow line Seyfert 1 galaxies. What makes this source so really in particular interesting is that during the Rosat-Or sky survey, it was a bright X-ray source. It was had one count in the Rosat-Or sky survey in the PSPC. And not only that, it was the softest AGN that we saw in the entire Rosat-Or sky survey. Now, after that, we did pointed observations with Rosat a couple of years later. And you can see the timeline here. This is between 1990 and then there are the Chandra observations later on. So these are all Rosat observations. It dropped down by a factor of 400. And that is really unusual. While we see variability in AGN, and Maurizio gave an excellent talk here on AGN variability. Typically, AGN vary by factors of 3. That's not unusual. If you have a narrow line Seyfert 1 galaxy, it might be even a little bit higher. And some of the narrow line Seyfert 1 galaxies, they can show spikes. They show all kinds of things by factors maybe of 30 or 40 even. But 400 is very, very unusual. Now, some of these things could be driven by accretion events, like you have a tidal disruption event or an accretion disk instability. We have seen these in some other AGN or in galaxies. This is probably not the case in this case, because we saw also a lot of activity with SWIFT. I started monitoring the source 15 years ago with SWIFT. And we saw in about 2 years, between about 2009 and 2011, we saw a lot of activity going on in this source. And this is not what you expect from a tidal disruption event. So when we talk about variability, and Maurizio talked about this earlier, was there could be 3 causes for this. There could be absorption, there could be reflection. So you change the reflection on the accretion disk, and that changes your variability. Or it could be simply feeding the black hole. You throw more stuff on the black hole, it becomes brighter, or you starve the black hole, then it becomes dimmer. So we see these strong changes in active galactic nuclei. And here's a comparison. This is just from Rosat observation of my sample of about 100 active galactic nuclei. And WPVS really stands out of this. This is down here with a factor of 400. This is the line of a factor of 10. This is a factor of 100. And we had other sources that come close to this, like IC 3599, which showed accretion disk instabilities. And then this one, this is a tidal disruption event, RX day 1624, and WPVS down here. But the big question we always had is, what is really going on in the source? And this shows the SWIFT monitoring that we have done since that I started 15 years ago with SWIFT. And on top is the X-ray flux or the X-ray count rate. And in order to detect the source, actually, you have to add really years of data together, because in a single observation with SWIFT is totally unobservable. It has a count rate typically of about maybe 10 to minus 4 counts per second. And with SWIFT, you are really in the noise here. You cannot do this. You really need Chandra for this. And I will get to this later on, because we are, of course, at a Chandra meeting. SWIFT is equipped also with a UV optical telescope. So it allows you simultaneous observation, not only in X-rays, but you can also get them in 3 optical filters and 3 UV filters. And that's shown down here. So these are the 3 optical filters, V, B, and U. And then you have the UV filters, W1, M2, and W2 up here. And you can see how the source is varying over the last 15 years. Here's a zoom in of the last 5 years, starting from 2015 and going. The last observation was just from a few weeks ago. So you can see how the source really evolves over time. So we have a strong variability, not only in X-rays that we saw from the Rosat data and then compared to other observatories, but we also see that there is intrinsic variations in the UV and the optical data as well. So the big surprise was here that when Karen Lely took a fuse observation in 2003, this source was strongly absorbed. And this is something that you expect from a broad absorption line quasar. So when we got this spectrum back from fuse 17 years ago, on the gray curve here, you see a typical canonical quasar spectrum, and the black one here is WPVS. So you're looking really in an outflow here, in a strong, very strong outflow here. Which is very unusual. I mentioned this earlier. This source really shouldn't exist because you expect these kind of outflows, these broad absorption lines, these broad absorption line troughs only in high luminous and high black hole mass AGN. But WPVS 007 or 007 has a black hole mass that is comparable to the black hole mass in our galaxies, only 4 million solar masses. We did also a couple of HST observations. That's what Karen Lely did. Starting in 2010, there was also an observation in the mid-1990s by Bob Goodrich. And what you can see is over here in this plot is this is the 2010 observation, the blue one here, which shows this really deep absorption trough of the carbon 4 line here. This is the emission line carbon 4, and this is the broad absorption line trough. What makes this also interesting is that this broad absorption line trough is variable. This is something you cannot observe in a typical broad absorption line quasar, although I should say that a postdoc from Neil Brandt, she did a study on broad absorption line quasars, and there were a couple of them that showed similar things, but on a much, much longer time scale that you can see in this narrow-line Seyfert galaxy. So what Maurizio said earlier is because the time scale scales with the black hole mass, we can observe things in WPVS that we will be unable to do this in a high mass, high black hole mass broad absorption line quasars. Now, what is also interesting is here that the color, thank you, the color changes. So when the source appears to be red over here, these are the colors over here in this plot here. So when we measure red colors in the UV spectrum, then the absorption disappears. And that is, counterintuitive at first. But when it is blue, the broad lines appear. And what happens here is that we are actually looking at the torus. And the torus, of course, is not this solid donut shape that we often envision. But when we can look directly onto the source, we see the strong outflows, which means we see the strong outflowing gas here. And if it is occulted, when the source it becomes red, then we only see the low luminosity outflows. So the strong absorption troughs, they disappear. Chandra observed the source 4 times, and the Chandra observations are marked here in red. It's very low. We need Chandra actually to detect the source. There is no way we can detect it with Swift. But when you look at the Chandra data, when you look a little bit more closely into the Chandra data, so there's the count rate up here, which is relatively small here in 2002 and then also 2015 and 17. But the color seems to be changing here. And at first, you think, okay, maybe intrinsically the spectrum is changing, but it's actually not, because what we are looking at is the increasing outflows, the outgas of the Chandra detector, or on the Chandra detector, we get this plastic layer on the entrance window of ACES. And but when you take this into account, the only way to actually get that the count rate remains the same is that intrinsically the source has become brighter, and this corresponds with also the Swift data. So what we have to do in the future is, first of all, I hope I showed you that this is really a unique source, because it is really the link between narrow-line Seyfert galaxies and the broad absorption line quasars, something that was suggested by Neil Brandt 20 years ago, and then by Todd Bowerson in 2002. What we need to do is we have to continue with Swift, and I will continue monitoring the source with Swift, because I'm also waiting that the source becomes flaring again, and then I can trigger an XMM observation if possible. We also need additional HST and Chandra observations if possible, and possibly making a long exposure with Chandra of something like 500 kiloseconds to actually get also the underlying spectrum. Thank you very much.
Great, thank you, Dirk. That was excellent. Very interesting source. If we have any questions for Dirk, please enter them into the Q&A. I had a question. It's interesting that you could see the effect of the contaminant in your observations, but also.
Oh yeah, you do, because you would expect that the spectrum remains flat, and it does not, or you see about the same hardness ratio. If there's a change in the hardness ratio, you would maybe also see some more variability, that it becomes softer, but what you are seeing is really that it hardens. And at first thought, okay, well, this is maybe interesting because the source becomes harder, but in reality, it's not. When you think about it, you have the build up on the layer of the ACES window that you are seeing here.
Right. We have a question from Abdu Zagbi. Can you say something about the inclination of the system? In narrow-line Seyfert 1s are thought to be typically observed at low inclination, and the figure you showed us seemed to suggest a high inclination.
That's correct. I mean, for typical narrow-line Seyfert 1 galaxies, we always assume a low inclination angle where you look directly onto the accretion disk, directly onto the source, and that's why they maybe also appear to be so soft. But for this one, we are looking at a very high inclination angle where you look into the winds. This might be a reason why we don't find too many of this, or this might be so far the only source that has shown these broad absorption line outflows.
Great, thank you. That's all the time we have for Q&A.
Thank you,
the
guys.
next speaker to start sharing their slides. Thanks again, Dirk. Our next speaker is Dharam Law, who is coming to us from the National Center for Radio Astrophysics, TIFR, and is going to talk to us about flaring in NGC 4869 and the effect of Kelvin Helmholtz instability. Take it away, Dharam.
Thank you first, and thank you for organizing this Chandra time domain workshop. Thanks you all for giving me this opportunity, and more importantly, thanks to Paolillo and Grupe to set up the stage for AGNs. And I would talk about an object NGC 4869, which is residing in Coma cluster of galaxies. And this is a powerful AGN, unlike radio quiet AGNs, which we were discussing, or variability of Seyfert galaxies. So I'll be telling a little bit about flaring in NGC 4869, what are radio observations and Chandra X-ray observations telling us about this object. Since I'm talking about effect of Kelvin Helmholtz instability, I wanted to give a strawman's picture of what Kelvin Helmholtz instability is all about. So this typically occurs when there is a velocity shear in a single continuous flow. For example, in this case, a buoyant incense smoke, and this plume accelerates upwards, it triggers Kelvin Helmholtz instability. And in radio jets, you have jets emanating out from core, hitting the ambient medium, and the beam essentially flows back, and this creates a contact discontinuity. So when there is a velocity difference across the interface between two fluids, velocity of a shocked ambient gas and backflow plasma material, which are at different, and there is a potential for creating strong Kelvin Helmholtz instability at the contact discontinuity. So this is the latter, which I'll be talking a little bit about. In this case, what is happening? So what kind of media these radio jet propagate through? So they can propagate through X-ray coronae, which are of size scales similar to what this host galaxy size scale is. So in this picture, I'm showing NGC 4874, which is compact dominant CD galaxy in the Coma cluster, and the radio contours are shown in magenta. The top panel is soft band of Chandra, and the bottom panel is essentially HST image of the same source. And contours are identical at both places. So what you see essentially is radio jet traverses through the ISM of the host galaxy, and then it can inflate. Is it a Kelvin Helmholtz instability? One doesn't know, and a little bit talk about when we talk about NGC 4869. Radio galaxy, in particularly powerful radio galaxies, they reside in either field or cluster environments, and I'm giving few examples in this slide. So one is 3C200, which is on the leftmost panel, which is essentially where your background is the Chandra image, and superposed on it are X radio contours. And what you detect here is core emission, extended lobe emission, and in etc. The second is 4C 19.44, powerful quasar. Again, the contours are radio and the background image is Chandra image. And in this case, what you detect is largely southern hotspot, northern hotspot, southern radio lobe, radio jet emission, and also background cluster emission is also seen in this case. On the right panel, these are not great images, the IC310 and ESO 137-006. These are residing in cluster environment. And again, so my point is jets are traversing not only through ISM of the host galaxy, they are also experiencing the cluster gas environment. And this is what I'll be taking up in NGC 4869. And this is the radio galaxy, which I want to talk about. And it's a head-tail radio galaxy mapped with upgraded GMRT at band 3, which operates between 250 to 500 megahertz. So 300 to 500 megahertz, 200 megahertz wide single band image. And what you see is like two jets trailing behind. So you have a head and the tail forming. And the tail is essentially doing something which I'll explain in detail in the next slide. And then it bends sharp by almost 70 degrees. At this location where it bends from the direction of propagation, it also flares up, or there is a sharp ridge-like feature. Okay, so in this is the same source, but the image is at band 5, which is from L band of upgraded GMRT. The diffuse extended emission is resolved out. The inner part for the head until the bent region is displayed, and there is a zoom-in version of this. So what you see is a head where you essentially comprises of nucleus and the two jets traveling on opposite side. The forward jet essentially bends because of ramp pressure, and then the two jets trail behind. So you have a head, and the second region is inner region, which is of the order of from head to 20 kiloparsec in size. This is a conical shaped feature. And subsequently you have an intermediate region, which is where the jet further expands. And probably in this case, the jets are also twisted around. So there is a pinch-like formation. And further on, there is an outer flaring region, which is of the order of 40 kiloparsec to 100 kiloparsec. This is second region of expansion. And as I mentioned in this, from intermediate region, outer flaring region to further on, it's a bent tail region, which is from 100 kiloparsec to almost 200 kiloparsec sized region. And you clearly see the flaring part. I want to next walk you through a little bit about the radio spectra of this thing. Fortunately, in this 200 megahertz band image, you could have in-band spectral index. It's the first time you could do it for such a source. So what I'm showing is you typically in a radio spectra shows progressive steepening of spectra as a function of distance from the head, and spectral index increases. So it's flat near the head or the core region, and then it steepens out. And this is largely due to synchrotron cooling. But the in-band spectral index, what I'm trying to show is showing the red feature, which is spine, and an enveloping green-like feature, which is sheath. And spine is relatively flatter compared to sheath. And the three dotted lines, which are drawn over there at distances of 25 kiloparsec, 40 kiloparsec, and around 70 kiloparsec. And the spectra of these are what I'm showing in the bottom panel. So bottom panel, essentially, they're all put together just to show that the inner region is steepening, getting steeper and steeper as you move from head to farther regions. But the spine is getting steeper further as you move further and further away. I'll repeat. So there is a clear presence of two component spectral index in the inner, intermediate, and outer flaring regions. And more importantly, there is a presence of flat spectrum spine and an enveloping steep spectrum sheath feature, which have different spectra. And the transverse cut spectra shows that the spectrum of the enveloping sheath is relatively steeper than the spine at any given location. Fine. So next, let's move to first ISM jet interaction. So this image is the two mass G like all three band color image. Superposed on it is the radio contours from the band 5, the L band image. And what I'm seeing is essentially a radio jet interacting out of the ISM of the host galaxy. ISM of the host galaxy is of the order of 6 or 8 arc seconds, which is just in kiloparsec of the order of 3 to 4 kiloparsec. So the central AGN has significant impact on the ISM of the host galaxy. And jet power is typical, the kinetic power of the jet in powerful radio galaxy typically is 10 power 43 arcs per second. And so what I want here, what is likely is happening is that jet carries fair amount of energy, but it's not dissipating the small ISM of the host galaxy. And if at all it is doing something, it is essentially stripping off some fraction of this ISM, which is seen in similar galaxies in the coma cluster like NGC 4848 or IC 4040 in the coma cluster, that only small few percent of ISM gets stripped out as they move into the, or as the jet radio AGN trap. Jet emanates out of the ISM. Next figure, this I'm now talking about jet interaction with the ICM. So what I'm saying, the location where the jet flared up, or a collimated jet had flared up. So I'll say that the X-ray image is showing the coma cluster, which is unrelaxed and has gone recent cluster merger. We know this. And at this location where I'm trying to show with dotted magenta or red stuff with arrows is a location where you see a surface brightness edge. The radio contours, the red one is L-band image, which I had shown you earlier, and the yellow one is the band 3, 250 to 500 megahertz image of the same source. And flaring is mostly seen in low frequency, the band 3 image, because most of this low surface brightness emission is resolved out in high frequency.
3 minutes.
Sure. So further on, so what I'm doing here is I'm showing on the left around this edge how the surface brightness is changing, and in the top panel and in the bottom panel I'm showing is how the density and temperature are changing. So this exercise is largely to determine that the surface brightness edge that I'm seeing, is it a cold front or a shock front? And in this case, it's a mergers picture, and this is hinting towards the cold front. So I'll repeat that what is happening is, therefore, it seems that the ram pressure condition, which is happening in this case, indicates stability against the ablation of radioplasma in the ISM when it was leaving it. But in case of here, it is essentially flaring up the radio jet. And this is supported by hydrodynamic simulations which are conducted by Loken and his collaborators, which shows radio galaxies through the hot intra-cluster gas, develops Kelvin Helmholtz instability, which manifests, or in other words, in radio images, you will see this as a flaring. So I want to repeat that. A collimated jet, when it encounters a surface brightness edge, it flares up, and this is largely because of Kelvin Helmholtz instability. Further, please recall that when I showed the transverse resolution radio spectral index, there was essentially a sheath which was steeper spectrum compared to spine. And there is also mass loading. It essentially entrains material from the ICM. And this is seen in, for example, 3C31 by Lang and Bridle. Now, it is not clear that this entrainment, which transfers momentum to the ambient gas, is also adding to the Kelvin Helmholtz instability, but it's not clear. This needs to be explored. So this is the summary slide where I'm just saying what are the characteristic things. We see a sharp bend, or at this location we also see a flaring. The spectra shows progressive steepening. In addition, it also hints to transverse velocity structure with fast-moving spines surrounded by slower-moving sheath. And we reported a flaring of a straight collimated jet, which is due to Kelvin Helmholtz stability. Thank you for your attention.
Thank you, Dharam. That was really interesting. Do you have, if we have any questions for Dharam, please enter them into the chat, into the Q&A box. I was going to go right into a question I had for you. So you have to do these radio and X-ray observations. Do you have to do them simultaneously, or does it not matter if there's a longer?
So this source is particular radio galaxy, they don't show variability. And so the simultaneity is not an important thing. And particularly in this case where I'm talking about radio propagation of a radio jet in a media, in two different media, one is ISM of the host galaxy and the cluster gas environment. These are, like I should say, on time scales of hundreds of million years, if they at all change. So we are talking about observations which are made in a year or few years apart, which should not. So variability or simultaneity is not an issue here.
Not an issue. Great. Any other questions for Dharam? If not, we can also open, I'll ask you this question, but we can also open the question for all members of the session today, if you have any questions for any of them. Dharam, we have a question from Agniva. How do you exactly know that Helmholtz instabilities is the dominant and at the surface brightness edge?
Okay, so so this is a little bit of speculation. Let me share my screen again. So right, so this is a little bit of speculation. Largely, these hydrodynamic simulations have shown where a collimated jet with certain Werner trend crosses media which have different densities and temperatures, they flare up. And we saw this first in 3C449 observationally. And this is second object to my knowledge where we are seeing this thing. Now, I missed the question completely. Can you please repeat it?
How do you know that Kelvin Helmholtz instability is dominant at the surface brightness edge?
Okay, largely from simulations is where this has come as an input. Now, in the beginning when I was showing this little model that there is cases where velocities of a shocked ambient medium and backflow material which are very different. There's a case for strong Kelvin and Helmholtz stability at this. So observationally, such things were seen for backflow models. And I do not know if I'm answering, but this is what I have.
Yes, it sounds like Agniva was asking what exact feature you're looking for, and they see now.
Right.
Great. Thank you.
Thank you.
Okay, any more questions for any of our speakers today? We have a question for Dirk from Maurizio. Dirk, there is a D. Sico et al. Work with Neil and Maurizio from 2018 that shows similar variations in BLA QSOs, but you said that these were not the same as those you observed in narrowline Seyfert 1s. I was wondering if the latest SDSS observations are revealing more similarities. Dirk, you're muted for some reason, but you're not.
You know what? When I put this microphone up, it's muted. Thank you for reminding me. It happens sometimes. Yeah, thanks, Maurizio, for pointing out this paper. I have this check later on. We will keep an email contact and discuss this, I would say. I really have to check this out because, it's good to know that there are more variability papers on broad absorption line quasars. And you're right. I mean, the SDSS, which has multiple observations on some fields, can detect, of course, these kind of variabilities as well. What I said about WPVS 007 is that the timescales are short because the black hole mass is short.
Great. All right. If there's no more questions, then I think we can say goodbye. Thank you, everybody, for joining. Remember that our next session is on AGN as well, and it'll start at 2 p.m. And let me just show you what that session looks like. There it is right there. Again, starting at 2 p.m. Eastern time here in the US and whatever time for you. Thank you all for joining us again. I hope to see you there. Bye.
Bye. Thank you very much.
Thank you.
Bye.
Thanks, Rodolfo. See you
Yep.
later. Bye.
Bye.